With Doubtnut, get instant video solutions to all your maths, physics, chemistry, and biology doubts. Just click the image of the question, crop the question, and get instant video solution. Download Doubtnut app today.
Hello everyone, let us start with our question. In this question, what is given? A long hollow insulating cylinder of radius capital R and negligible thickness has a uniform surface charge density is given as to be sigma. So it is a hollow and it is having a surface charge density sigma, and it is rotating about its central axis with a constant angular velocity omega. Okay, sigma is the surface charge and omega is the angular velocity. Okay, so if we draw our situation, so it would be we just draw. So let's say this is the one side and this is our another side. Okay, so these are the ends. Okay, and it is revolving about the this angular central axis at angular velocity omega. Okay, now what will happen? Now the charge crossing a imaginary line of length L on the surface of the cylinder parallel to its per unit time is given as to be omega sigma this R into L. Okay, this is the value which they are saying. Now for example, if we draw a line here, if we just take a line, okay, let us draw a line at this surface. Okay, now so what will happen? So for example, there is a charge on this line. Let's say that charge is the positive charge. Okay, then what will happen after a complete revolution? This charge would come back to its original location. Similarly, if we draw a line here, so the charge at here, if we just tilt this, or if we just rotate this, then after one revolution it would be coming back to its original position. Okay, then we can say that our this I, which is defined as charge, so in the A part, because it is given as charge per unit time, so for a complete rotation we say that time would be equals to t for complete rotation. Okay, now t is given as to be, if it is rotating with angular velocity omega, then it would be equals to 2 pi by omega. This is the value of the time period. Now what would be the value of the charge? Sigma is the surface charge density. Okay, so if you multiply with the total area, it would be equals to 2 pi r into L, because it is the surface charge density. So the surface area, this would be a this cylinder. So basically we have drawn it on the this side view, we have just drawn. So it would be here, it would be just circular. Okay, now so if we see this, so 2 pi would be cancelled, then it would turn out to be sigma into omega r into L. So this is the value of the charge per unit time. So it would be, so this option is correct option. Now the magnetic moment is given as to be pi omega a r cube into L. Okay, we can just find the value of the magnetic moment. So in the B part, so if we see here in this part, so when it is rotating, so what will happen? So it would be forming a current loop. So it would be forming a current loop. So this charge, for example, this charge is completing a turn, so it forms a loop. Now this charge also completes a turn, it also forms a loop. So each and every charge which is on this cylinder would forming a current loop. Okay, so in this portion there would be many current loops. So we can say that our this magnetic moment would be equals to I net or I equivalent this current into what is M given as to be I into A, I multiplied by area. Now what is the equivalent charge? We know that the charge which has been equivalent current into A. So what is the value of the equivalent current? It is the current which has been possessed or which has been produced due to the charge flowing in this conductor. So it would be equals to sigma into omega r into L. Okay, and what is the value of the area? Area A is the area of the cross section of the loop. So loop would be like this. This would be the loop. So what is the area? This is the area, which is equals to pi r square. So if we solve this, then it would turn out to be, so it would be pi sigma omega L r cube. So if we check our second option, pi omega sigma r cube into L, pi omega sigma r cube into L, B is also a correct option. Now what will happen in this case? So we can just assume that by seeing this, we can just assume that there are several loops here. For example, this is one of the loop, this is another loop, then this is another loop, till here, till total length there are loops on this hollow cylinder. So basically it is just behaving as a what? It is just behaving as a long solenoid. Okay, it would be behaving as a long solenoid. We can say that in this we can just say that our rotating hollow cylinder behaves as a long current carrying solenoid. Current carrying solenoid. Okay, because there would be several loops which would be forming, so it would be just like a current carrying solenoid. We need to find the magnetic field intensity. Now due to solenoid, in the C part, we can see that in the solenoid, what is the value of the magnetic field? So magnetic field is given as to be mu naught n into I, where n is number of turns per unit length. Okay, so n into I, what would be this value? This is number of turns per unit length. Okay, and this is the current. That means the current in the loop. Okay, so we can say that it is just equals to n into I is equals to our equivalent current. Why? Because there would be the total number of a loop which would be forming here on this length L. If we just take the product, it would turn out to be the equivalent current, or we can say that it would be equals to mu naught. And what is the value of the equivalent current? It is sigma into omega into R into L. So if we check the magnetic field intensity in the C option, so mu naught sigma omega RL, so it is given this mu naught sigma omega, but it is given as to be R square. So this is wrong. Now if the direction of the rotation is reverse, magnetic field at the point will also be reversed. So for example, if these are the positive charge and we are rotating it clockwise, okay, so what would be the direction of the magnetic field? It would be in the upside by using right hand thumb rule. Now if we are changing the orientation, if we are rotating like this, so the direction of the current is in the upward. Now if we are changing the orientation and we are rotating like this, so by using the first this right hand thumb rule, we can get the direction of magnetic field to be in the negative direction. Okay, so D option is also the correct option. So what are the correct option? A is the correct option, then B is correct and D is correct. So hope you have understood the solution. Thank you.
For class 6 to 12, IIT JEE and NEET level. Trusted by more than 5 crore students. Download Doubtnut app today.